Hello, my name is Alex Robb, and I am presenting a video abstract for our paper in the Journal of Photochemistry and Photobiology A entitled Metal Ion Linked Multilayers on Mesoporous Substrates, Energy and Electron Transfer, Photon Upconversion, and more. To begin, photo-induced energy and electron transfer is useful in a wide variety of applications and is possible through a wide variety of synthetic structures. There are also many options for facilitating intermolecular interactions, but to hear more about them, please read our review. In this review, however, we will be focusing on self-assembled multilayers via metal ion linkages. This multilayer assembly strategy was first introduced in 1988. Using planar substrates, layers of alkyl phosphonates could be formed by linking the molecules together with zirconium linking ions. This strategy was a simple and modular means of combining molecular species on surfaces, allowing either hetero or homogeneous films to be produced via stepwise soaking. This process can be repeated n number of times to produce a film m number of layers thick. Planar substrates are not the only ones capable of using this technique. In 2012, the first example of a multilayer film on a mesoporous nanocrystalline metal oxide was published. It was found that using a mesoporous substrate greatly increases the absorption cross-section, allowing for characterization using standard spectroscopic techniques, and it greatly increased the viability of this strategy for solar energy applications. Unfortunately, the porous nature of the nanocrystalline films limits the number of layers that can be generated, and we assume that the maximum number that can be produced is less than 4. Despite this, metal ion linked multilayers on mesoporous substrates have been used in photocatalysis, charge separation junctions, DSSCs, and in cross-surface energy migration. In this perspective, we recount our efforts to utilize these layer-by-layer assemblies on mesoporous substrates to manipulate interfacial electron transfer rates, generate directional energy transfer cascades in light harvesting devices, facilitate and harness molecular photon upconversion via triplet annihilation, and we would like to close with a summary and potential outlook. In trying to manipulate interfacial electron transfer rates, we studied a common strategy for slowing recombination rates, increasing the spatial separation between the die and the surface. This can be accomplished through either IALD or through synthetic modification. However, ALD requires high vacuum equipment, and synthetic modification can involve difficult synthetic pathways. Thus, in 2015, we introduced multilayer assemblies as an alternative strategy for influencing electron transfer dynamics. In this strategy, we sought to separate a chromophore from the surface by adding photophysically and electrochemically inert aryl diphosphonic acid bridges. This achieved the same goal as ALD in synthetic modification, but without high vacuum deposition equipment or complex synthesis. Through TA, we discovered that the BET rate decreased with the increasing bridge length, which indicates that the molecular bridge acts as a tunneling barrier. And through steady-state and time-resolved emission measurements, we also found the same trend of decreasing rate of injection and electron injection yield with increasing bridge length. Knowing this, we then incorporated the bridge ring layers into a DSSC utilizing N3 dye and iodide-triiodide redox couple. We found that the decrease in electron injection decreased the overall photocurrent, but the bilayer sterics decreased the rate of recombination nearly 5-fold and allowed for a small increase in VOC. Unfortunately, the loss in photocurrent greatly outweighed the gain in voltage and fill factor, and the overall performance of the device decreased. Now, understanding the role spatial separation would play in a bilayer, we then investigated the role the metal ion may play. The majority of the multilayers in the literature were using zirconium and zinc linking ions, where the metal ion are assumed to be photochemically and electrochemically inert. However, when copper was used, the copper ion introduced an additional quenching pathway, but still allowed for injection. Thus, we propose that the copper ion may serve as an electron hopping intermediary between the die and the metal oxide surface. Knowing that this intermediary step was possible, we then incorporated several different cations into the bilayer film. Similar die surface coverage were achieved for all films, but different stabilities were observed. For example, the K-desorption on iron and zinc was greater than the K-desorption rate for zirconia and RUP. The K desorption rate on TiO2 is 20% greater than the desorption rate for zirconia oxide. In looking for some form of a relationship, there was no trend between the size, charge, and coordination number of the ion and desorption rate. However, K desorption increased almost linearly with the ionic contribution to the hard-soft acid-base interaction, which suggested that electrostatics were at play. It was also determined that the zirconia bilayers were the most stable on both metal oxides. Finally, the device performance produced similar results to the bilayer JV testing, except that the competitive quenching of copper, ion, and manganese caused notably lower photocurrents. Thus, if one is looking to produce a metal ion linked system in which the metal ion is an inert scaffolding, then they should choose one of the other metals. With an understanding of spatial separation and metal linking ions, we then sought to produce bilayer dye-sensitized solar cells. Monolayer dye-sensitized solar cells are subject to transmission losses and decreased light harvesting. In order to combat this, bilayer DSSCs hope to absorb a broader portion of the solar spectrum, but surface area limitations prevented these films from achieving such large improvements. Absorption can be increased by increasing film thickness, but it increases the likelihood of recombination and also slows the diffusion of redox mediator into the porous films. Thus, a metal ion linked multilayer that is not surface area limited can achieve complete surface coverage of both dyes, allowing for additive absorption. We sought to do just this with our first example of a bilayer DSSC using N3 and 1M dyes. When produced, the absorption spectra was indeed the sum of the two spectra. With an increased absorbance, the bilayer outperformed all of the other control devices that contain just monolayers of the individual components on their own. The JSC, VOC, and efficiency increased by 10%. The bilayer was also 1.5 times more efficient than the co-deposited film. As well, the incident photon to convergent efficiency IPCE spectra showed that the bilayer device was the sum of the monolayer devices. Beyond just increased absorbance, these dyes were also chosen such that they were capable of favorable directional energy transfer, and the following mechanism was proposed, where you can excite the 1M dye, which will energy transfer to the N3 dye, or you can just excite the N3 alone. From there, electron injection, electron transfer, and dye regeneration can occur. This bilayer DSSC demonstrated that metal ion linked multilayers can be an effective strategy for broadening and increasing absorption, slowing back energy transfer, and improving device performance. It is worth noting that this system could be greatly improved through the design of chromophores with nearly unity interchromophore electron energy transfer yields and with high injection yields. Something that was interesting in the previous study that we chose to explore deeper was the increase in VOC that was observed from simply coordinating zirconia to the dye on the surface. We coordinated a variety of metal ions to the dye and observed no change to the redox potential, E00, or excited state electron potential, but we did see a decrease in JSC and increase in VOC for the majority of the films. Thus, adding a metal linking ion is a simple means of increasing VOC without the need for surfactants, synthetic modification, or metal oxide treatment. We wondered if this could be due to electrostatics, so we utilized 3 redox mediators, one positive, one neutral, and one negative, to observe if there were any significant differences. We observed that there was a 100 millivolt increase in the VOC regardless of the charge, and thus suggested that the sterics of having the metal ion on the surface potentially plays a larger role than electrostatics. Concluding our work on Cascades, we then sought to produce a Singlet Fission bilayer DSSC. Singlet Fission could potentially increase solar cell efficiencies beyond the theoretical limit of 33%. Thus, we bound a carboxylated derivative of a previously published Singlet Fission dye to a metal oxide film, where we were able to conclude that Singlet Fission was occurring, and then we coupled a low-energy triplet sensitizer to the dye. With 470 nanometer excitation, we observed a complete quenching of emission relative to RUC directly on the surface, and a nearly 100% efficient triplet energy transfer from RUC to the Singlet Fission dye. With Singlet Fission shown to be plausible, we investigated the opposite process, Photon Upconversion. Upconversion had been previously presented in the literature either via co-deposition or heterogeneously, but we sought to introduce the first TTA-UC mechanism a metal ion linked bilayer. After stepwise soaking, we had additive absorption, suggesting that both dyes were present on the surface of the zirconia oxide film. From there, excitation at 532 nanometers exhibited blue upconverted emission with a quadratic to linear intensity dependence that is symptomatic of TTAUC. In order to produce a DSSC, we had to change the metal oxide and introduce a redox mediator and cathode. Once produced, the photocurrent enhancements for the bilayer were more than 5 times greater than its individual parts. The current density relationship also exhibited a 2-to-1 slope change indicative of TTAUC. This was record-setting for TTAUC devices, but in order to further improve device performance, the efficiency-limiting processes had to be quantified. Thus, through a variety of spectroscopic techniques, we elucidated the rates of several key processes. Notably, the triplet platinum porphyrin to acceptor energy transfer rate limited the triplet energy transfer yield to 30%, which increased to 100% would result in a 3-fold increase in photocurrent. Also, electron injection from the acceptor is much faster than FRET, thus suggesting that the majority of the losses occur prior to injection. Trying to understand this platinum porphyrin to acceptor energy transfer event, we systematically modified the acceptor molecule. We found that platinum porphyrin to acceptor triplet energy transfer and cross-surface migration were dramatically affected by the structure of the acceptor. Most notably, the triplet exciton diffusion constant varied by 2 orders of magnitude for at least one of the acceptor molecules, presumably due to either the low steric hindrance and/or the relative orientation favoring face-to-face stacking of the acceptor molecules. Looking to break our previous record efficiency, we then sought to produce a self-assembled tri-layer DSSC. This tri-layer achieved record-breaking photocurrent enhancements via the use of an additional singlet sensitizer that absorbed light in the transparency window. From the photovoltaic testing, we saw that under solar radiation with 455 nanometer long-pass filter, the singlet sensitized tri-layer generated photocurrent that was more than 3 times greater than the bilayer film. The singlet sensitizer also contributed to the photocurrent generation and produced a 3-time current enhancement from 440 to 530 nanometers. Direct excitation of the singlet sensitizer showed a quadratic to linear intensity dependence that shows that the singlet sensitizer is involved in the TTAUC mechanism. And finally, the ith value was 2 times lower than the bilayer and nearly 30 times lower than solar flux. Finally, we sought to utilize a quantum dot as the triplet sensitizer in the upconversion bilayer. Quantum dots are known for their ease of synthesis, small singlet triplet gap, and readily tunable energetics. They also have been previously shown to facilitate upconversion. Thus, we used a quantum dot as a sensitizer, and we observed that the JSC enhancements are more than the sum of its individual parts. We also saw an ith value below solar flux and an ith value on par with platinum porphyrin. However, the quantum dot bilayer produced more than 6 times less photocurrent than our standard upconversion bilayer. With all of this said, in our work on upconversion, we had produced a metal ion linked upconversion bi and tri-layer. We gained insights into the underlying rates, and we even introduced a new sensitizer into the mix. In conclusion, we find that the length of the inert molecular bridge and the nature of the metal linking ion can have a dramatic effect on the electron transfer rates, excited state quenching, and overall device performance. We found that bilayers can be used as an alternative to co-deposition in order to realize broadband absorption and low-energy triplet sensitization in Singlet Fission devices. And finally, we found that metal oxide-bound multilayers are also an effective strategy for facilitating and harnessing TTAUC in an integrated upconversion solar cell. From all of our work, we found some generalizable trends. That steric bulk provided by the multilayers between the semiconductor and the dye redox mediator effectively slows unwanted back electron transfer processes. We found that multilayers can avoid surface area limitations, enable additive bi- and tri-layer absorptions, and increase light harvesting efficiencies. We also found that inter- and intra-layer energy transfer are influenced by both the energetics and the structure of the dyes, as well as the nature of the metal linking ion. For potential outlook, we've determined that selecting, designing, and fine-tuning the molecules in each layer for specific tasks or applications will be crucial in maximizing future device performances. We also want to understand how the multilayer's thickness and pore size can influence diffusion rates of potential redox mediators. We're interested in understanding what role, if any, the second molecular layer may play in influencing intermolecular interactions in the first layer, and we're interested in gaining structural information about the bilayers at the mesoporous interface. With that being said, I would like to thank you for listening to my video abstract, and I would like to invite you to follow us on Instagram and Twitter at Hanson FSU. And thank you again for listening.